Welcome to Study Loop.
All right, we're looking at question 16 in chapter 22, and it is essentially a series of true, false questions. Our first statement is SIF6 a thing? And to get at that, we have to look at expanded octets. So in other words, does silicon form an expanded octet? Well, the requirement for an expanded octet is that valence electrons must have a principal quantum number of greater than or equal to 3. If we go to our periodic table and look at the electron configuration for silicon, we see that for silicon, its electron configuration is neon core, and then 3s2, 3p2. And looking at this, we see that we do indeed have valence electrons with the principal quantum number greater than or equal to 3. So silicon can form an expanded octet. And the reason for that is that when we form single bonds to things, we take all of our valence electron orbitals and combine them into energetically degenerate hybrid orbitals. And in order to have more than 4 orbitals to work with, we need to bring in d orbitals, and those d orbitals require n equals 3. Bit of a typo there. Okay, now let's move on to the next one. In B, the question is whether or not silicon can form stable compounds SiH2, SiH4, and SiH6. And the answer to that is no. That's the case for carbon. But if we take silicon and do this, we get a bunch of unstable compounds, which isn't really mentioned in the textbook. But the thing to remember here is that it is true for C2H2, which is just acetylene, C2H4, and C2H6. These, in fact, are very common compounds that you'll see when you start talking about organic chemistry. So this one is false. Okay, the next question is we're going to look at two compounds, HNO3 and PO4, or excuse me, H3PO4. So we got nitrous acid and phosphoric acid. Give ourselves a little bit of room here. So we're looking at the central atom oxidation state of these compounds. And so to do that, we need to find the oxidation state of the central atom. And so we'll begin by assigning our priorities, or our priorities. And oxygen is a higher priority than nitrogen. And so that means that it will get its preferred oxidation state of -2. So we've got -6 for the nitrate, or nitrous, +1 for the hydrogen. And this guy's -5, or +5, excuse me. It's a neutral compound, so that must be +5. Doing the same thing for the phosphoric acid. That'll be -8. That'll be +3. which of course means that for charge balance, this must be plus 5. Both N and P are plus 5. And since our original statement was that they had different oxidation states, this one must be false. And lastly, the question is whether sulfur is more electronegative than selenium. And to answer that's really simple. We just have to look at our periodic table. And if we go to our periodic table, we see that sulfur is above selenium. And our periodic trend for electronegativity is that it increases as we get closer to fluorine. Fluorine is the most electronegative element. And so because sulfur is closer to fluorine, this statement is true. Well, it's not because it's closer to fluorine, but our periodic trend will tell us that it's closer to fluorine, so its electronegativity then will be higher than selenium. Okay, so to summarize, our first answer is whether SiF6 2- is a thing, and the answer to that is that it's true, and that's because silicon can form an expanded octet since its valence electrons have a principal quantum number greater than 3. We have 3s2, 3p2. We can have an expanded octet. For B, the question is whether silicon can form compounds with 2,4. Oops, bit of a typo there. I just realized I didn't include the 2 in these, so excuse me for that. It's essentially asking if silicon can form these binary compounds very similar to alkanes, alkenes, and alkynes for carbon compounds, and that's false. These compounds aren't stable for silicon. C asks us whether the central atom had the same oxidation state for nitrous acid and phosphoric acid. And we saw that that was that they have the same oxidation state, so the statement that they're different is false. And then for D, we're asking if sulfur is more electronegative than selenium. It turns out that's true, and we can surmise that from our periodic trends. All right, I hope that was helpful.